And then we have to zoom because it changes its size. And there's a focus. Okay, so what we've done with the data on the rotating beam is we went into Excel. Did a graph of theta versus t based on observations of different people at different points. Okay. Now there are uncertainties in this observation because it's kind of hard to actually keep up with the marks and the X's and stuff like that. So it's very easy to have data points that are a little bit off. But we can, we've got simple devices that will take data. All we got to do, there's a plug on this thing. You won't see that in the camera. There's a plug here. It plugs into one of those things over there. And we spin the thing, it'll take all the data. Then it'll pretend it knows what the velocity, angular velocities are in the angular accelerations. All it's doing when what it measures is positions. That's all it measures. It can't measure velocity and it can't measure acceleration. It has to take the data on position and figure out what the most likely velocity, angular velocity function and angular acceleration functions are. Okay. Well, we want to understand that because that tells us, it gives us information about how reliable those angular velocities and angular accelerations are when we plug it into the machine. We don't just take that literally. It's an experimental course. Okay. And we want to appreciate how the limitations of the apparatus affect our conclusions. So we use the most limited apparatus we can find, which is you, which is us. Okay, I include myself. Well, no, there's even more limited stuff that we could have used. Okay, but you're limited enough that we get an idea of how valid these approximations are. Okay, so we got 5 points. And then we did a quadratic approximation. Now, when we click on trend line, it automatically shows us a linear approximation, and it's clearly not linear. A quadratic approximation works pretty well. It looks exactly like this. It would minimize the average squared distances, vertical distances between the curve and the point. Okay. So I didn't do a real good job of hitting that, but yeah, this is kind of low, and these 3 are a little high. Changed it and move the curve a little bit that way would be much better. Okay, so any one of the approximations might have looked like this. Quadratic approximations would have looked very much like this, but more accurate. Okay, the cubic approximation would look more like, very much like this. We flipped from one to the other and saw how the curve changes, just tweaked a little bit. Okay. And when we went to the quartic approximation, 4th degree approximation, it tweaked a little bit more. When we went to the 5th degree approximation, it looked exactly like that, but it got all wiggly on it. This is because we only have 5 points. Okay, 5 points with a 5th degree approximation. The polynomial has to adjust itself so it goes perfectly through all 5 points, which means it can have 4 relative maximum and minimum and inflection points. Okay. Now, it would be interesting. This little beyond the scope of what we do with analyzing data. I'm just going to mention it, but if you're not on top of this, it's kind of worth understanding. We could test that by saying if this, we could test the quartic approximation to see if there are inflection points. Okay, if there are inflection points, that means the derivative is going to wiggle. Okay, which means that this probably isn't the best approximation to use of the polynomial approximations. There are all kinds of approximations that could work very well if I could talk. But the quadratic and cubic approximations are probably pretty good. Now we can test that a little bit. Okay, so here is our quadratic approximation. Here's our cubic approximation. I had to write the numbers really small here, but we know what they are. Okay, and you can read those. The screen's going to be accurate enough. But that's 2 times 10 to the negative 6. That's 2 times 10 to the negative 5th. I wrote all the zeros. And yeah, here's the rest of it. Okay. If we take the derivative of the quadratic approximation, we get the angular velocity that would relate to an angular position function that agrees with the quadratic approximation. And that's pretty close, we think, to the behavior of the actual system. Okay, so we take the derivative, we get omega t, and the derivatives are straightforward. I'm going to sign for the negative 0.006. But we get this for omega t. And then our derivative of that, which will give us our angular acceleration, rate of change of the angular velocity. Gives us this. Okay, now our cubic approximation. Here we have it. We take the derivative of this, then we get got enough zeros there. Okay. A small coefficient on t squared, a small but order of magnitude bigger coefficient on t, and a 0.26. Now the 0.26 and the 0.307 aren't real close, but they're in the same ballpark. That would give us our t equals 0 angular velocity. Because we plug t equals 0 in, anything with t on it goes away, and we're just left with a constant. So this tells our initial angular velocity would be 0.307. Here it would be 0.26. So there's a difference between what these approximations are telling us right there. Also, the coefficient of t here is not nearly the same as the coefficient of t here, because you got this t squared thing. Okay. And what we get for our angular acceleration then would be negative 0.000012t. Now the fact that we have a 1, 2 here and a 1, 2 here, just coincidence. And then we get negative 0.00004. So our angular acceleration doesn't appear to be very linear, very constant. That's a little disturbing because as t gets up to 200, this number gets pretty big. You get a pretty big angular acceleration compared to what we see here. So I haven't totally processed it. I mean, I didn't, you know, we did this just based on random, not random points, but on selected points in a data set of 38 points and selected points from different observations. Okay. So it could be something going on. Now, what people got from the exercise, we took each person's individual curve, estimated slopes, graphical estimates, hand-drawn graphs, yielded our omega versus T graphs. Reasonably linear, so they kind of look like maybe this. In a straight line, did a pretty good job of approximating. Now, my question is, the equation of that straight line pretty close to this equation? Well, I'll pause for a second, just ask you what the vertical axis intercepts were when you sketched your omega versus T graph. Well, the y-intercepts that people got graphically just by drawing tangent lines and so forth were generally on that 0.06 and 0.6. Okay. Now that's not real close to this. Then it's not real close to this. But it's not that far away either. Okay. So something about hand drawing and stuff, you expect that much deviation. Okay. What about the slopes? What are the slopes of your hand-drawn graphs? You know, what we're seeing is there are intercepts. You know, our calculated slopes are not inconsistent with what we see here, but not all that close. And again, that's just due to anomalies of the whole graphical process. When we did Excel, it's our delta theta over delta t versus t mid. Remember, t mid is the midpoint between your two times. And this is the delta theta over delta t for the interval. You can review what we said last time about that. Those graphs violate my favorite t, but we're not using this. I think it came out something like this. There's a anomalous point up here and other points. Okay, so it wasn't a great yet, but it definitely had a slope. But Excel chose to represent that slope as negative 0.001. didn't give us any significant figures. Okay. So I don't know what Excel thought it was doing, because it's giving us 4 significant figures and everything else, but just 1 from the coefficient of t squared. So what we got there isn't very reliable, but this is very consistent in shape with this graph. Okay. So we're going to maybe want to do a little more observation, a little more analysis of the functions, but we're going to do that with you doing the Excel, getting your quadratic, cubic, and quartic approximations, and taking these derivatives. Okay, that's all. So that's fairly straightforward. If you have trouble with that, let me know.